Hello, my name is Rishabh Ghodke. I'm a PhD student at the Delft University of Technology, where I work with solar energy for charging electric vehicles. Here we will look more closely at solar car parks for charging electric vehicles, which is an example of a complex socio-technical system. The physical system of this solar car park consists of several components. One of the main components here is the aluminium carport. It is the structural element with load-bearing capacity. Mounted on top of the carport are the solar modules that convert solar irradiance or sunlight into direct current through the photoelectric effect. Direct current cannot be directly fed into the public electricity grid. In the late 1800s, transporting direct current at low voltages was the norm, but was associated with extremely thick cables and high resistive losses. However, the invention of the transformer helped to increase the voltage of alternating current for transportation and reduce it again at the point of use. This resulted in fewer power plants, lower material use for cables, and lower losses during transmission, drastically reducing the cost of electricity. Therefore, alternating current was chosen as the type of electricity for public electricity grids and remains the type of electricity used in the public grid today. Today, however, LEDs, batteries for electric cars, and electronic devices like computers all use direct current. Rectifiers at the point of application convert alternating current to direct current here. A solar inverter is therefore installed to convert the direct current generated by the solar modules into alternating current for usage in the electricity grid. Vehicle chargers use both solar electricity as well as electricity from the grid to provide reliable charging despite the variability and intermittency of solar production. The electricity in the system is metered at several points. For example, the solar power produced is metered at the inverter, while each of the electric vehicle chargers meters the power delivered to connected vehicles. It is also possible to control the solar power generated or the rate of charging of the cars through these devices. These are aspects of the operational layer of the system. The parking lot operator can generate revenue through the feed-in of solar electricity to the electricity grid. Charging of vehicles at public locations is also a paid service. So billing customers for the electricity delivered to their vehicles is a way of generating revenues for the solar car park. An example of this is a solar car park located near a shopping center. Here, electric vehicles can be charged while people do their shopping. They use their charge passes to authenticate their identity and pay for the electricity used. This is an aspect of the economic layer. And finally, there's the policy layer, the legislative background. Carport structures in public areas need to conform with legal guidelines to ensure the structural integrity of the construction. They need to be able to house cars of various manufacturers and sizes to ensure the safety of the people who use them. Vehicle drivers need to have licenses and their vehicles need to comply with safety and environmental standards. But also from a more social perspective, there are normative rules governing people's behavior. For example, parking spaces that have charging facilities are marked and should not be used to park non-electric vehicles. Or when connecting the cable to charge their vehicles, drivers should ensure that the cables are not a nuisance for pedestrians. Further, when the batteries are full, it would be considered to move the vehicle to allow access to other electric vehicles in more urgent need of charging. These layers are also clearly interacting with each other. For example, the users can authenticate their identity through a card-based user interface. This is where the social layer meets the physical layer. This authentication process informs the operational layer about whether the user has the permission to charge at this location and tells the economic layer whom to send the bill to. Similarly, if the charge point is at a public location, it may need to be shared among several vehicles. If drivers leave their cables plugged in at the socket for a long time after the batteries are full, it prevents other electric vehicle drivers from making use of the same public charge point. In such an event, the operational layer can be programmed to react if the current falls below a certain threshold for a specified duration of time while the vehicle is still plugged in. A notification may be sent to the driver, or by involving the economic layer, the driver may even need to pay an idle fee to discourage this kind of behavior. The car park system also interacts with the external environment. The amount of solar energy generated depends on the sun's position in the sky and how cloudy the day is. The amount of electricity charged depends on how far the vehicle was driven to get there and the charging habits of the driver. The revenue earned by the parking lot depends on both these factors, and these, together with the cost of electricity purchased from the grid, can influence the choice of one type of energy management algorithm or another. And if there's a short circuit, the system operators may receive an email or a text message informing them that there's an issue. And they may also be provided with an initial diagnosis. These interactions between the layers and the infrastructure that supports them provide several opportunities for making the system smarter. If all the charging points at a given location are occupied, a navigation app may automatically guide a driver to another location with more charging points which are available at this point of time. This ensures that drivers are not worried about whether they have enough energy in their cars to get home. Such automated decision making can also be implemented for deciding when to charge if it knows your schedule, or can even be programmed to drive the car on its own. Solar car parks for electric vehicle charging are one example of a socio-technical energy system. Another example, also focused on mobility, are mobility sharing programs, for example bikes, scooters, and cars. Let's go deeper into the case of bike sharing programs available at stations in the Netherlands. Each station includes a parking lot for bikes that can be used for anyone with a public transport subscription. Users getting off trains or trams can issue these bikes for traveling the last few kilometers to their destination. This smart card, which is linked with the identity of the user and the bike key, are both scanned at the time of checkout. When the bike is returned to the station, the bike key is scanned again and the user is charged based on the duration of use of the bike. Such smart systems can help with mobility issues of the future and improve the efficiency of our energy usage. Fewer bikes or cars are needed, which reduces material and resource use, takes up less space for parking in our cities, and improves user interactions. A broader outlook covering all the elements involved, their relations with each other, and the interaction of the system with the outside world can help designers and decision makers to deal with the complexity inherent to socio-technical systems and align them with the objectives of the energy transition.